All right, so right now we're gonna calculate the Laplace transform of f of t equals t squared. Remember, the Laplace of f of t is, this is the formula we just worked out, integral from 0 to infinity of f of t times e to the negative st dt. I do apologize, my s's look a lot like 5s. So I'm going to try and avoid using 5s for a while, but eventually we'll get that in there. So if I want to do the Laplace of t squared, it's this thing. Before I do that, I want to back up a little bit, right? I want to remind you of some of the things that we have done. One, this is the formula. I used it to solve a differential equation. I need a massive list so that I can do this step right here. I need to know how to take the Laplace of all these different functions so that I can do this. And that's what we're working on right now. And it takes like kind of some time to work all those out. But once we get that, which is what we're working towards, then you'll be like, whoa, I can solve this differential equation. So I just want to continually remind you guys of that because you can get lost in the wait, what's going on, right? This power series versus Laplace, really that's just working out the formula, right? So once we have this formula here, right, which is over there, and also down here, right there, we can start working out the Laplace transform of things. So that's what we're going to do right here. How do I do that integral? Well, this is why integration by parts is such an important topic from BC, because it shows up literally everywhere. So I need to do the t squared is going to be the derivative side. And then the int side is going to be my e to the negative st. So let's do the t squared. Let's derive it down. 2t, 2, 0. Now remember, this s, I treat it as a constant when I do this integral because s and t are totally independent variables. So I just treat s as a constant. It's totally fine. So I get negative 1 over s, e to the negative st. Next one is, it's going to be positive 1 over s squared, e to the negative st. And then my next one is going to be negative 1 over s cubed, e to the negative st. And then I'm going to go diagonally. I'm going to alternate my plus, minus, plus. Notice when I do these products, all these terms are going to be negative. So I'm going to use bad notation here. I'm not going to use limits with the infinities because it's going to get too complicated, and I think it's easier for you to see it if we do that. So this integral is equal to, it is going to be the product of those first two, negative t squared times 1 over s, e to the negative st. The next one is going to be minus again, 2t times 1 over s squared, e to the negative st. And then the last one is going to be minus 2 times 1 over, actually I'll write that as 2 over. The other ones I don't want to, but this one I will. So minus 2 over s cubed, e to the negative st. Is that correct? All of that evaluated from t equals, and I'm writing the t because there's two variables here and I want to be really clear about which one we're plugging in. T equals 0. And this is the spot where if I were doing it correctly, I would write t equals b and then I would use limit notation, but I'm just going to sneak my way in and write that infinity. So let's look at all these terms. I'm going to go like this. So what I'm going to do, I got 1, 2, 3 terms. So I'm going to write 1, 2, 3 things here, and then 1, 2, 3 things here. The t equals infinity will be here, and the t equals 0 will be here. I'm going to write out what they are, and then I'm going to explain why. 0 minus 0 minus 0. And then minus, I guess this should have a minus, 0 minus 0 minus 2 over s cubed. So let me explain why all those pieces go away. And I'll maybe highlight a little bit. So let's see. When I plug in infinity to this term, I get that 0 right there. Because e to the negative infinity goes to 0. And remember, oh, this is important, from all this work that you may have been like, why do we care about this s? Why is he doing all this, right? Well, s is positive, right? So down here, remember, s is greater than 0. If s could be negative, then this might not be an exponential decay. But since s is positive, then it's e to the negative number times t. T goes to positive infinity. It goes away. So the next term, this 0 right here comes from the same thing. That gives me this. It's multiplied by a polynomial. It doesn't matter. This term goes to 0. Same thing here. This guy gives me that. Now the other ones get zeroed out for different reasons. I'm plugging in t equals 0 to this stuff. So the first term, this guy, actually I shouldn't do the negative, it's just the t squared gives me that. Then, look, this 2t here gives me that when I plug in 0. And look, this one, that one right there, that is the only term that survives. When I plug in t equals 0, oh, you should see that e to the negative st evaluated at t, well, I guess I shouldn't do that one, sorry. This e to the negative st evaluated at t equals 0 gives me e to the 0, which is 1, right? So when I evaluate this guy here at my t equals 0, this guy at 0, this term goes away. But this term survives because it doesn't have the t from all the integration by parts stuff. So I get this guy right there. I hope you see that. We get a lot of these cancellations, and I don't want you to just start writing zeros like that, right? I want you to see where they come from, right? So you can write it just the way that I wrote it here, but I want you to make sure that you actually do get 0 with things. What does that give me? Well, look, all these guys are gone, and then I get a double negative on this, and I just get 2 over s cubed. Now, if you think back to way earlier in all this stuff, we did the, I showed you the Laplace chart, and I tried to point out that Laplace of t squared, and what was on there? It was a 2 over s cubed. I hope you see that, and we're going to work out a couple more, and I'm going to do that in a little bit different way. So hopefully you're good with that. And I'm going to pause. What I want you to do now is I want you to calculate 2 Laplace transforms. I want you to calculate the Laplace of t and the Laplace of t cubed. What I'm going to do is I'm going to pause my video and do all the solutions, right? I'm going to do solution for number 1, and then I'll do the solution for number 2. Same way we would do if we were doing these board work videos. So I want you to try to do Laplace for t and check here, because I'm going to put it up in a moment, right? And then after you check that, if you need to walk through it, I'll walk through it, and then I'll give you another timestamp for when I do the Laplace of t cubed, and you can check that as well. You should pause now. You should pause now and try to do the Laplace of t, and then I will pop the answer up right here. So here comes the answer. Here's your work to check. You should get 1 over s squared. If you got that, great, and then just go on to the next timestamp that I list out somewhere for you, maybe in the video. In the whatever, I'll list it for you. But in a video or a Google Doc if I send this to you with a Google Doc. But here, now I'll walk through why we get 1 over s squared. I set up my integration by parts. I get t1 and 0 on my derivative side. I get e to the negative st, negative 1 over s, blah, blah, blah. Same things I had up above. It alternates and the s increases by a power. You should see that that pattern is going to happen anytime I do this integral. So maybe you can start thinking about what t to the n would be. But I get this thing when I do my products. Both terms are negative. T and 1 over s squared, 1 over s, and 1 over s squared, Evaluate from t equals 0 to infinity. There's an exponential decay in each of these when I plug in t equals 0, so I get a minus 0 for the infinity piece, minus when I plug in t equals 0, this thing zeroes out. That's this first term here. And then this right here gives me my negative 1 over s squared. I get a double negative on that and get 1 over s squared. Hopefully that makes sense. And now I'm going to do the Laplace transform for t cubed. So go ahead, hit pause, make sure you've done that, and then it will come up in a moment. So your answer for the Laplace of t cubed should be 6 over s to the 4th. If you got that, awesome. I want you to go forward one more bit to the next timestamp that I list and do what I ask you to do there. If you want to hear me walk through it, then go ahead and keep listening. So I do some integration by parts, derive, integrate. Same pattern, alternating, powers increase. Same pattern, I multiply out front, right? So I get all these products, right? T cubed with a 1 over s. All of them are going to have an e to the negative st, and all of them are negative. 3t squared with a 1 over s squared. 6t with a 1 over s cubed, and then 6 all over s to the 4th. When I evaluate these from t equals 0 to infinity, I plug in the infinities first. Exponential decay on all of them. So all 4 of them are 0. Minus, this gets evaluated to 0, 0, 0. This is the only one left. So I get this, and remember this piece evaluates to 1, so I get 6 over s to the 4th. A double negative here and here cancels to become positive, and I get 6 over s to the 4th. So the last thing I want you to think about, what do you think the Laplace of t to the n power would be? What I'm asking is, could you take the Laplace of any polynomial, t to any n power? And keep in mind, this would have to be an integer power. It's going to be more complicated if we have a decimal or fractional power. Think about this one up here. Actually, I'll write all of them. T, I'm going to introduce some new notation. T Laplace to 1 over s squared. So there's different notations that are good in different spaces or in different areas, right? This notation right here is this what I'm saying right here is exactly the same as saying a Laplace with a t and just n equal 1. So t squared Laplace is to 2 over s cubed. T to the 3rd Laplace is to 6 over s to the 4th. So what do you think t to the 4th would Laplace to? And how do you see the patterns up here that would convince you that not just like guessing that it would be true, but yes, I know that I would get fill in the blank, right? So what would that Laplace do? What would t to the 5th Laplace do? Without doing all the work, what would it Laplace do? And then what would t to the nth Laplace do? Because if we can get those formulas, then we can just use them. And that's going to help us as we're trying to solve those differential equations. Hopefully you're on board with this. Y'all are doing an awesome, amazing job, and I will see you soon.